Okay, here we have our next example. In this example, we will see another important ODE that arises from applying Newton's second law of motion, F equals ma. This model in particular plays an essential role in structural dynamics. So here is our example. We want to consider the classic spring mass system with external and damping forces. Let's see what the statement of the problem says. A mass M is attached to a spring with a spring constant K, and it is free to move along a single horizontal axis. But by this I mean the mass M moves horizontally. It will not move vertically. It will not move out of the plane. This mass M will move in horizontal, along the horizontal axis in horizontal direction. In addition to the spring's restoring force, this is the force that a spring applies to the mass M when the spring is stretched or compressed. It applies a force to the mass M, and I will give you more information about that. In addition to that force that is applied to the mass M, we also consider the possibility of friction. The friction, for example, with the floor, hindering the motion of the mass M. This friction force is usually referred to as the damping force. So we consider the possibility of having damping force here. Also, we consider the possibility of an external force being applied to this mass M. This external was a given force. I'm going to denote it with F E X T of t. It may change with time. For example, this can be sine of 10t, right? There is some given external force that is applied to the mass M. It may be zero, but it may be non-zero, and I want to consider the possibility of having this external force acting in horizontal direction on the mass M. So what is the goal here? The goal here is to derive an ODE governing the position of the mass M as a function of time. So I want to know exactly where this mass M is at any given time. I want to have an ODE. By solving that ODE, I can find the position of the mass M at any given time. That is the goal. Let me be very clear about the assumptions that we have for this model. I went over some of the assumptions, but let me just clearly list the main assumptions here. So one, the spring here is ideal. Well, what do we mean by that? We assume that our spring is massless in the sense that the mass of the spring is negligible compared to the mass M that is attached to the spring. And also, we assume that our spring obeys Hooke's law. At least for a small displacements, this assumption is a legitimate assumption. And what does that mean? What do we mean by Hooke's law? By Hooke's law, we mean this force that a spring applies to the mass M, this restoring force, is proportional to the displacement of the mass from its equilibrium position. So what it means is that this Hooke's law is telling us that the force that the spring exerts on the mass is proportional to the amount of stretch or compression of the spring. In the equilibrium position, when the spring is not stretched or compressed, the spring will not apply any force to our mass. And when it is stretched or compressed, the magnitude of the force that is applied to the mass is proportional to the displacement of the mass from the equilibrium position, to the amount of stretch or compression in the spring. That is what the Hooke's law says, and it agrees with reality, at least for a small displacement. The length of the unstretched spring, we assume it is L. So in the equilibrium position, we assume that the length is equal to L. When there is no external force applied and nothing is moving, the length of the spring is L. This is the unstretched length of our spring. So that was one assumption. The fact that the force exerted by the spring on the mass It follows the Hooke's law. And also the length of the unstretched spring, we're going to assume that it is L. As we discussed, we are going to assume that the motion of the mass is restricted to one dimension. There is no vertical motion. There is no motion out of the plane, right? Everything is happening in the horizontal direction. And this makes sense because the external force and also the spring force and also the friction force, they are all applied to the mass in the horizontal direction. The damping force, that friction force, we're going to assume that the magnitude of that the damping force is proportional to the velocity of the mass. And also the direction of that is the opposite of the direction of the motion. It points in the opposite direction of motion, the friction force, the damping force. The constant of proportionality, so I'm assuming that the magnitude of the damping force is proportional to velocity. What is the constant of proportionality? We call it the damping coefficient, and we're going to denote it by gamma. This is some given constant to us. Gamma is a known number, and that is how we can relate the damping force to the velocity of our mass m. And as I mentioned, the external force is also given to you. Somebody gives you a specific formula for the external force that is applied to the mass m. So this is a known function of time. It's not necessarily constant, but it is given to you. For example, it is a cosine 10t. That is the external force that is applied to the mass m. And also we are going to assume that other than the spring force, the damping force due to friction and the external force, there is no other forces applied to this mass m. So we are going to ignore, for example, the effects of the air resistance. There we are assuming that they are negligible compared to the forces that we are considering here. So just again, to be very, very clear, what is the goal here? Our goal is to determine an ODE for the position of the mass m. Position is a function of time, and I want to find a differential equation such that by solving that differential equation, I will know the position of the mass m at any given time. Derive the ODE and ODE governing the position of the mass m as a function of time. That is the ultimate goal here. I'm not going to solve the ODE. I just want to derive the ODE, the equation that governs the position of the mass as a function of time. The position will be a function of time. All right, so obviously we are studying the motion of a body. We immediately think of the Newton's second law. And as we know, every time we want to apply the Newton's second law, we need to set up a coordinate system, give a name to the variables of interest, variables that are important in Newton's second law, and then draw a free body diagram, make sure that we understand all the forces that are applied to our body. Here, the body is the mass m, the body of interest is the mass m. And then write the Newton's second law to come up with the equation of motion. So I'm going to follow our program. This is the program that we always follow in these problems where we are interested in the motion of an object. So to apply the Newton's second law, first I'm going to set up my coordinate system. So let me draw what we had. We have these walls, and we have our spring. K with the constant K, that this K is the constant of proportionality for that relates that connects the force, the restoring force of the spring to the displacement, to the amount of stretch and or compression of the spring. And then we have the mass m. And I'm gonna choose my the coordinate system as follows. The horizontal direction, that will be my x coordinate system, x-axis, and then vertical y. Now, we can also consider the z-axis. Z-axis and the y-axis will not play any role. Here, everything is happening along the x direction. the motion is happening in one direction. And as a matter of fact, as you know, when the motion is happening in one direction, we don't really need to work with vectors. We can use sign numbers for our quantities of interest, such as position, velocity, acceleration, force. But as you saw in previous problems that we did together, I prefer working with vectors. I think actually it makes things simpler when we are working with vectors and we are considering this three-dimensional situation. Of course, we know that there is nothing happening in the y direction, there is nothing happening in the z direction. So let me give a name to quantities of interest here. I have my position vector, obviously. That is the most important thing here for the mass m. I'm going to denote that by r of t. And here we only have motion in the x direction. So it will be a component times I. I is the unit vector in the x direction. Remember, I is 1, 0, 0. Unit vector in the positive x direction. And I have mentioned this multiple times in these videos. When we have motion in one direction, sometimes people refer to this x of t as position, right? That is okay. So we can, when we talk about position, we can talk about this position, we can mean this position vector, or we can also mean this x of t. This is the position of the mass m. All right, and then what will be the velocity? Obviously, the derivative of the position. The velocity vector, it is equal to x prime of t. We have to take the derivative with respect to t, I. Now, if you like, you can denote this by v of t without arrow on top, right? You can call this v of t the velocity. So when someone says velocity, they may refer to this velocity vector, which is on the left, or they may just refer to this quantity, a scalar quantity that you see on the right, little v of t without arrow on top. They both are okay when the motion is happening in one dimension. Generally, when you say position, velocity, acceleration, that means vector. You have a vector, but when the motion is happening in one dimension, it's okay. It is a standard to use the term velocity for both the things, that what you see on the left and what the number that you see on the right, v of t, the scalar quantity that you see on the right. By a scalar quantity, I mean a number. All right, and a of t, the derivative of the velocity, will give us the acceleration. So that is x double prime of t, I. There is nothing happening in the j direction, in the k direction, j being 0, 1, 0, k being 0, 0, 1. Nothing happening in those directions. You can think of it as plus 0, j plus 0, k. I'm not writing j and k because nothing happening there. And this is our a of t without arrow on top, the acceleration, the scalar acceleration. Or so far so good. So I introduced my coordinate system. I gave names to the quantities of interest, the position, the velocity, the acceleration. These are the things that will play a role when I want to apply the Newton's second law. And what about the free body diagram? So what are the forces that are being applied to the mass m? So let me list the forces. Forces applied, exerted on, applied to the mass m. So one of them obviously is this the external force as a function of time, and it is applied in the horizontal direction. So you can say that this external force as a function of time, it is indeed some number. I'm gonna call that number FEXT. EXT stands for external without arrow on top, for following the conventions that are used above for R of V of t and A of t, and then multiplied by I. I is the unit vector in the positive x direction. So if this quantity FEXTT is negative, that means that at that moment of time, this force is, the direction of this force is in the direction of negative x-axis. If this highlighted quantity at some moment, at some t, is positive, that means that at that moment of time, your external force is pointing in the positive x direction. That is actually the reason that I'm not drawing the vector. Because if I draw a vector, then I have to choose a direction, but the direction is changing here depending on time, depending on the value of fex dt, and this is given to you. The statement of the problem told us that the formula for this external force is given to you. So this is one of the forces that is applied to our body. Another force that's applied to our body, obviously, is the damping force. That damping was another force. Let me write that as FD, F subscript D. I'm going to use F subscript D for the damping force. Again, it is a function of time. And according to our assumption, it is proportional to the velocity with the constant of proportionality gamma. So we have the velocity vector, the constant of proportionality gamma, and it points in the opposite direction, right? That is how the friction force works. This V gives you the direction of motion, but the damping force works in the applies in the opposite direction. So that is why you see this negative sign here. If you like, you can write this as negative gamma x prime of t I, because this x prime of t I is v of t, as you can see above. We have the formula for v of t above. So this is our damping force, and it depends on time. You can put t here if you like. And what is the other force that is being exerted on the mass m? The spring force. So I'm gonna call that Fs. Is that okay? Fs. And remember, the spring force depends on the amount of stretch or compression in the spring. What is the amount of stretch or compression? The position of the mass minus the unstretched length of the spring, which we denoted by L. Now, this is the amount of a stretch or compression. If it is positive, that means that we have a stretch in the spring. If it is negative, that means that we have compression in the spring. And obviously, this force is in the horizontal direction, I. And please notice that if the spring is stretched, if we have the stretch, let's say that this is the length L, and now this is x of t, and this is the diagram for the case where the spring is a stretch. Then this restoring force, the spring force exerted on the mass m will point in the negative x direction, will point leftward. It will be to the left. So in the case that we have a stretch in where this is positive, the spring force is pointing in negative I direction. So I'm going to put a negative sign here as well. Negative here. And of course, the constant of proportionality, which we denote by K. This is called the spring constant. So you can do the same analysis to make sure that this formula works for the case where a spring is compressed. The formula works the same way. So let's say that now this is the mass m. So this time, this is x of t. The unstretched length was L. And now that the spring is compressed, the spring force will point to the positive x direction. But again, this formula will work because in the case of compression, xt minus L is a negative number. When you multiply by this negative sign here, will become positive, which is correct, because when the spring is compressed, the spring force will point in the positive direction. So excellent. We have all our forces and the formula for all our forces, and now we can apply the Newton's second law. So in this example, instead of drawing the free body diagram, I listed all the forces that are applied to the mass m, and I explained why I was hesitant to draw a diagram in this case. Okay, so now we apply our Newton's second law. By Newton's second law, of motion, what we know is that ma, the mass times the acceleration, is equal to the total force. The force of the spring, the damping force, the external force acting on the mass m. I'm writing the Newton's second law for the mass m. On the right hand side, I have the total force applied to the mass m. On the left hand side, I have ma. So let's use the information that we have gathered so far. A is x double prime of t I, right? That is the acceleration vector A, as we discussed previously. The spring force, we just went over this, is negative k. K is a given constant. It depends on the properties of the spring. The bigger the k is, the stiffer the spring is. It will be harder to stretch or compress the spring. Negative k x of t minus Li, that is Fs. And then we have Fd, the damping force. We have it exactly here. We previously discussed what it is. Negative gamma x prime of the I. So actually, let me write negative gamma x prime of ti. That is our damping force. And then what about the external force? Here we have it. This is given to you. This one will be given to you in the statement of the problem. This FEXTT is a formula that is given to you in the statement of the problem. You know what function that is. The only unknown here is x of t, position of the mass at time t. So let me, we see that we have I everywhere. So on the left hand side, right hand side, we have I. Let me remind everybody that you could have considered J and K here as well, but it would have been 0J, 0K, right? So we have on the left, we have a combination of ij and k. On the right, we have a combination of ij and k. The coefficients of the coefficient of I on the left must be the same as the coefficient of I on the right. The coefficient of j on the left must be the same as the coefficient of j on the right. The coefficient of k on the left must be the same as the coefficient of k on the right. Here we only have I. Now, what is the coefficient of I on the left? It is mx double prime of t. What is the coefficient of I on the right? Negative k x of t minus L minus gamma x prime of t plus f e x t t. And let me just play with this a little bit, rearrange the terms. I want to have all terms that involve x or x prime or x double prime. My unknown is x of t on one side. To do this, first let me distribute the negative k. So we have mx double prime of t is equal to negative k x of t plus kl. And then we have negative gamma x prime of t. And then we have FEXT T. And now I'm going to bring everything that involves the x or its derivatives to the left. So mx double prime of t plus gamma x prime of t plus k x of t is equal to the external force, magnitude of the external force. It can be positive or negative, of course. This is a function that is given to you, plus KL. This will be our second order ODE. Then again, remember, M is a given constant, gamma is a given constant, K is a given constant. This is, as a matter of fact, a second order linear ODE with constant coefficients, a second order linear ODE. And we have a step-by-step procedure for solving problems like this. It's a non-homogeneous ODE because the right-hand side is not zero. A second order linear ODE, right? That is what we have here. I think we can, if we wanted to, we could have solved it. We could have like proceeded further to solve this. but I'm not gonna do that. Just one more last comment that I wanna make here is that if you want, you can introduce a new variable. If we introduce x tilde t as x of t minus L, then we can write m x tilde double prime t, because the derivative of x tilde is the same as the derivative of x, because L will disappear. L is a constant number. And then the first derivative, the second derivative will be the same, gamma x tilde prime t, and then k x of t minus kl, that will be k x tilde t equals the external force. So this is another way of writing the same thing, but for the unknown x tilde. If you find x tilde, you have x of t. It's like you set when you set up your coordinate system, instead of setting up the way we did, you make sure that the origin is at the equilibrium position of the mass m when there is no external force. Folks, now you see that if the external force is zero, then this equation becomes a homogeneous equation for x tilde of t. All right. I think this is good enough explanation for the spring mass system at this point.